When ChatGPT answers a question, it feels like magic, like something is actually thinking in there. But under the hood, it is doing something far simpler than you think. Every large language model, every GPT, every Claude, every Llama is, at its core, a very, very sophisticated version of autocomplete. The one on your phone guesses the next word. These models guess the next word too, on a scale almost impossible to grasp. That single idea explains nearly everything. How they work, why they are so impressive, and why they still make mistakes. So here is the question this video answers. What is actually happening inside these models? By the end, you will understand the machinery well enough to see exactly where the hype ends and the real engineering begins. And once you see it, you can never unsee it, because it is far more ordinary and far more impressive than the sci-fi story suggests. First, you need to understand that these models do not read words the way you do. They process language as tokens, small chunks of text. A token is rarely a whole word. It is often a common word, sometimes even a part of a word. For example, the word unbelievable might become 2 or 3 tokens. Un, believe, and able. The model sees a stream of numbers, one for every token, not letters and not full sentences. This chopping is done by a tokenizer, and a common technique is called byte-pair encoding. There is a rough rule of thumb. In English, 1,000 tokens is roughly 750 words. So when people talk about a model's context window, whether it is 32,000 tokens or 128,000, what they really mean is how many chunks of language it can hold in mind at once. Get past the numbers, and tokens are just the atomic unit of everything an LLM says or reads. So what does the model actually do with all those tokens? In 2017, a team of Google researchers published a paper with a famous title, "Attention is all you need." In it, they introduced a new architecture called the transformer, and it changed everything. Before the transformer, models struggled to keep track of long passages of text. Words early in a sentence faded from memory. The transformer's key trick is called attention, a mechanism that lets every word look at every other word and decide how much it matters. When you read, "The animal didn't cross the street because it was tired," your brain figures out that it means the animal. Attention lets a machine do that mechanically, weighing every pair of words and building up an understanding of how they connect. That idea, simple in hindsight, is the engine at the heart of essentially every modern LLM. And because the transformer processes words in parallel rather than one after another, it can be trained on modern graphics processors at a scale older architectures never dreamed of. A transformer does not start out knowing anything about language. It learns. The learning process is called training, and it is where the scale becomes almost absurd. Developers feed a model enormous amounts of text, books, articles, and vast crawls of public web pages, billions of pages in total. The model reads through this text and plays a simple game over and over. Given everything so far, predict the next token. When it guesses wrong, its internal settings are nudged so it is a little less wrong next time. Repeat that across trillions of examples, and something remarkable happens. The model never sets out to learn grammar, facts, or reasoning, but to predict what comes next. It is forced to absorb all of it. That is the deep secret of these models. Understanding is a byproduct of prediction. When people talk about the enormous cost of AI, most of that cost is here. The computing power needed to run this training loop at all. All those tiny adjustments are stored as numbers called parameters. Think of each parameter as a small dial that tunes how the model responds. There are an almost unimaginable number of them. When OpenAI released GPT-3 in 2020, it had 175 billion parameters. To put that in perspective, a single model can have more adjustable dials than there are stars in our galaxy. The most capable open-weight models today reach into the hundreds of billions. Meta's Llama 3 family, for example, tops out at 405 billion parameters. More parameters usually mean a more capable model, because there are more dials to represent the complexity of language. But size alone is not intelligence. What matters is how well those billions of dials have been tuned by the training data. The scale is so large that no single person ever reads the model's settings. They are discovered by the training process itself. And a well-tuned smaller model can beat a poorly tuned giant, which is why the field obsesses over data quality as much as size. Now here is where people get the most confused. How a model answers the question. It does not compose a whole answer in advance. It generates text one token at a time. At each step, it looks at everything so far, your prompt plus the words it has already produced, and predicts what the next token should be. It assigns a probability to thousands of possible next tokens, then samples one. That tiny bit of randomness is why the same question can get slightly different answers each time. Each new token is appended, the model recomputes, and the process repeats until it hits a stop signal. This is called auto-regressive generation, and it is why a long response takes longer. Every single word is a fresh decision. So every answer you have ever gotten, from a one-liner to a 1,000-word essay, was built word by word, by a machine guessing what comes next. It is the closest thing computing has to a human speaking, one breath, one word at a time. And that is also why these models sometimes lie to you, confidently and fluently, because the model is optimized to produce plausible next tokens, not to be factually correct. When it does not know something, it does not say, "I don't know." It simply generates the most likely sounding answer it can. That is what researchers call hallucination. Models inventing facts, sources, and even whole events out of nothing. A model can invent a research paper that was never written, or a court case that never happened, all in perfect, confident prose. This is not a bug you can fully train away, because it is baked into the very mechanism. Fluency and accuracy are different goals. So the rule of thumb is simple. These models are astonishing at pattern and language, but they are not reliable sources of truth. They are a reasoning aid, not a replacement for checking your facts. And as these models get embedded into search, medicine, and workplaces, that gap between fluency and truth is the single most important thing to keep in view. So what should you actually take away from all this? First, understand what you are talking to. It is not a mind. It is a next token prediction engine on an enormous scale. That does not make it useless, far from it. It can draft, summarize, explain, and generate ideas faster than any human. But treat it like a brilliant intern. Extremely fast, occasionally wrong, and in need of verification. Second, respect the distinction between open and closed models. Some, like Llama, are openly released. Others are kept behind a company's servers. That choice shapes everything: cost, privacy, and who controls the technology. And third, keep the core mechanism in your head whenever the hype gets loud. Under the glow, it is just a machine guessing the next word. Understand that, and you understand more about artificial intelligence than most people who talk about it all day.